Okay, so this week we're going to talk about stock, steel, and strain. Basically the materials that we use for making things and properties of those materials. So, how do you choose a material? There are a couple of things to consider. You're trying to make a part or a machine or whatever. Usually these things are like cost of the material, depending on like how does it cost per gram or does it cost per unit volume, the weight of the material, so how heavy you want your part to be, how light do you want it to be, does it need to move fast or does it not going to move at all? Application requirements such as friction or response to stress. Like, is this part going to be in contact with other parts? Is it going to be under stress? Are you going to subject it to any kinds of forces and stuff? These are the kind of questions you have to ask when you're trying to create something. Because CADing it in Inventor is one thing, but what do you do after you CAD it? You have to start creating it in real life, right? So how do you intend to machine it? So what is stock? Stock is basically the starting piece of material that will become a part. Like if you're going to make something out of wood, generally you go find a plank or a log, and then you start cutting it out or carving it or whatever. Stock geometry should always be a consideration. So for steel, there are different kinds of stock geometries. Well, hot rolled usually refers to steel that has been just pressed at very high temperature. It's cheaper than cold rolled, and it's slightly deformed than cold rolled steel. Cold rolled steel is, however, stronger than hot rolled steel, but because it takes more effort to like make it cold rolled, it's generally more expensive as well. And it has tighter tolerances, and it's generally smoother. So stock geometries. So as I said earlier, if you're making something out of wood, how do you decide? Do you choose a plank or do you choose a log or something? So for steel or metals in general, you'll have different kinds of stock. Rods are basically long cylindrical. Sheets and plates are generally more important for their two dimensions, and they have a uniform thickness. And a bar is more like a plank of steel or metal. And the difference between sheet and plate is that, well, if you want to bend your metal, you want sheet. Plate tends to be 0.25 inches or thicker than that. Okay, everyone following along? Just give me some feedback. Any questions?
Could you repeat what bar stock was?
Okay, you see my mouse here? This is considered as a bar. It's kind of like a plank of metal.
Thank you.
Okay, cool. Any other questions? Moving on. Okay, metals. So aluminum. Aluminum is lightweight and it's kind of more expensive than steel, but it's also easier to machine. So you see these two parts over here. These kinds of details are like easier to create in aluminum because it's not as strong as steel. So these are the two most common kinds of aluminum we use, aluminum 6061 and aluminum 7075. Like, these are different alloys of aluminum, and they have different elements. So like 6061 has silicon and magnesium in it, whereas 7075 has zinc and copper in it, and a bit of magnesium. But anyway, the thing you have to remember is that the higher number generally means it's better. Like 7075 is almost as strong as steel. Now, steel is, of course, a lot stronger than aluminum, and because of that, it's also harder to machine. Like, if you're trying to cut up steel, it's going to take more effort than aluminum. It's also more ductile than aluminum. Does anyone know what ductile means? I thought we'll cover it in a while. So steel also has different kinds of alloys. Steel itself is an alloy of iron and carbon and other few additives. So 836 is the standard kind of steel that we use. There are others that are more ductile or more heat resistant depending on what you want. You can generally find a different kind of steel. Okay, everyone following along? Any questions? Okay, moving on. So plastics. In our studio or well, workspace, we tend to use 3D printing a lot. These parts and these parts are these are all just 3D printed, and this stock you see over here, this is the filament that we use in 3D printers. So choosing plastics is different than choosing a metal. So like, can anyone think of why you would want to use a plastic over metal?
Weight.
Weight, okay, that's good. Plastic is generally a lot lighter than metal. Anyone else?
Maybe you'd model something or like try out a design before you actually create the part you want to. Like prototype.
That's exactly what rapid prototyping is for.
If you don't want something to be rigid or as rigid.
So you're thinking if you want to make flexible parts, that's a good example. Yes, and there are certain kinds of filaments, 3D printing filaments, which can lead to flexible parts. So the two most common ones that we use are ABS and PLA. ABS is like the stronger plastic for 3D printing, but it's prone to warping. Warping means like it can bend when you're creating the part itself in a 3D printer because of the heat. And PLA, it works less. Usually you can get finer details out of PLA. And it's biodegradable. That is something I did not know, but yeah, that's a good thing too. So yeah, that's kind of the whole point of rapid prototyping. You create a prototype to see if the part will fit, if you need to adjust your tolerances or something. Like, it's your rough draft. And so, of course, if it's plastic, it's going to be a lot more brittle in comparison to other materials. Has anyone here actually 3D printed anything before or seen 3D printed parts?
I have a 3D printer at home.
Oh, that's neat. So you must have noticed something. The way 3D printing works is that it creates, like, it lays down the plastic in layers, right?
Yes.
Yeah, so the thing about layers is that it sort of creates, well, I can't exactly say a gap, but because the plastic is laid down in such lines, it's weaker in like when you apply shear stresses to it, but it's stronger when you compress it. So like it creates a sort of directional, like the properties of the material are different in different directions. Do you understand? Anyway.
Yes.
Okay, cool. Nylon. Yes, nylon is kind of tends to be flexible. And I'm kind of forgetting another flexible material that I've used in the past. Yeah, nylon has a large tensile strength, high impact resistance, HDPE. This is, I don't think we have this in our lab itself, but in the neighboring lab where all the big machines are, that's where we use HDPE. Yeah, it's also a generally cheaper plastic to use. So, stress and strain. Oh, is everyone following so far?
Yes.
Okay, cool. So yeah, stress and strain. Basically, what happens when you apply forces on an object? It moves or stuff. It does not move. What happens when it does not move? Well, something will still happen on the inside. And so stress is an internal reaction to the forces applied on the outside. It's measured in newtons per meter second, or basically force over an area. So normal stress is what happens when you just push down or pull on something along an axis or something. So in this example, as you can see, this rectangular piece is being stretched in here, or it's being compressed. So, whereas where shear stress is like applied in a direction that is parallel to a surface, like normal stress is perpendicular to the surface. Like this is the surface and the force is being applied here, or this is the surface, force is being applied downwards. It's perpendicular. Shear stress is parallel. This is the surface and there is a force being applied here, generally due to friction. So what happens if an object is under stress? It could get compressed or stretched. That means its size changes, and that change in size is called strain. Strain is a reaction to stress. And strain is considered as a ratio of the change in length to the original length, so strain does not have any units, it's just a ratio. Oh, I forgot these two. Stresses can also be applied if you're twisting something. So torsional stress is when you're applying two forces in the same, like clockwise or anti-clockwise pattern. These are two moments in the same direction. And bending stress happens when you have two moments in the opposite direction. So what do you think if bending stress is applied to this rectangular piece over here? Anyone? Well, it'll sort of turn into like a U shape. Okay. So this is called material science. This graph is a comparison between stress and strain. You would think that if you pull something, like its strain might be uniform, but that's not always the case. So over here in the initial part, you see that these lines are mostly straight, mostly linear. What does that mean? It means when you apply the stress, it stretches proportionally, or it compresses proportionally. What's happening afterwards? It kind of goes wonky. It means after a certain point, you cannot predict. Well, you can predict it because that's how we got the graph, but the deformation is no longer linear. So this initial region is called elastic region, which means if you stretch or compress something while you've only applied this much stress, after you remove the stress, it should ideally go back to its initial state. And this bump over here, this point over here, beyond which it just goes wonky, that's the plastic deformation region. If you've crossed this line, if you cross this point, your deformation will likely be permanent. And that is the main takeaway from this graph. So we have some materials looked at here. What do you think happens to glass over here? You stretch it, you stretch it, you stretch it, and then bam, it just breaks. You can't really deform glass too much because it will shatter. On the other hand, aluminum and carbon steel here, you can stretch them in an elastic region, and after you cross that point, you can sort of bend them, deform them. Of course, being steel and aluminum, you need a lot of energy to do that, but it is possible to deform them permanently. And let's take a look at rubber. It's not exactly linear. It is kind of similar. What do you think happens to rubber? Anyone want to take a stab at it?
Is it linear for a long time?
It's almost like you could, what do you call it, approximate it as a linear function. But as you know, rubbers are literally called elastic. Like, this is something you must have learned as a kid. So yes, rubbers only go elastic. Rubbers only have elastic deformation. Like, you can stretch it really long, or you can probably compress it also a lot. And after a certain point, it'll break. Just like if you have a rubber band nearby, you can just try it out yourself. Just stretch it out and break it. Okay. And there's just one more thing when it comes to metals. So there's this sort of ridge over here. What do you think this ridge is for? Like, anyone ever heard of strain hardening? So basically, when you start applying stress to carbon steel here, it'll stretch, it'll stretch, it'll stretch, and then it'll sort of go over this bump. If you release the steel after it's gone over this bump, it will kind of try to go back, but not completely. It'll sort of end up over here instead of its original position. This is called strain hardening, and if you do this repeatedly, like a few times, not too many times, but a few times, your material actually ends up stronger as a result. Whereas over here, after you cross over here, your steels will start necking. And that's the point where, like, it'll become really thin in the middle and become really easy to break. Yeah. Okay. Any questions here? I know this was like a long section. Everyone following along? Okay, I hope we're all good here.
You're killing it.
Okay, cool. Hey, sorry, I accidentally explained all of this. Okay, no, never mind. Yeah, breaking it down, pun definitely intended. So yeah, this is in general what a curve is supposed to look like. As you saw previously, glass and rubber sort of end at this point. This is the yield point because they do not have any plastic deformation. Yeah, these are not important to know, but they're certainly useful if you ever want to like study material science. I'm sure you guys will have to study at least one class of material science. But yeah, Young's modulus is this slope, like it's considered linear in this area, so the ratio is constant, and that ratio is the Young's modulus. And this is the yield point. This is the ultimate strength. The yield point is like the point where, like the point of no return, like you're getting to the plastic deformation part. And the fracture point, which is where it just breaks. Keep in mind that this is always just stress in one direction. Like if you stretched it too far and then applied another force in another direction, it would obviously break, but that's not what we're thinking of here. Okay. Brittle or ductile? So yes, I mentioned the word ductile before. What is the difference? So ductility is a sort of material property that we also consider when making things. A material that is more brittle will just break, like it will not deform as much and will break sooner, as opposed to a material that is more ductile. A material that is more ductile is more, what do you call it, more willing to deform. So glass is considered brittle because it does not have any plastic deformation at all. On the other hand, how would you describe rubber? Would you think it's brittle or would you think it's ductile? That's an interesting question. Because as we saw before, like rubber does not have any plastic deformation. It only has elastic deformation. So how would you describe rubber?
I want to say neither because it doesn't have any plastic deformation, but I guess the closest out of those two options would be brittle.
Well, that's a good answer, I'd say. Again, these terms are a bit subjective. Yes. Brittle does not necessarily mean it's weak, because a material could be brittle, but it'll still take a lot of energy to break. So the amount of energy you take to break something is the area under this curve. Like if you were to integrate this curve, you'll find out the area it takes to reach this breaking point. And so like if a material was brittle, it could just have like a really high curve, and that would mean that it takes a lot of energy to break. Whereas a ductile thing doesn't necessarily mean it's stronger. And yeah, brittle and ductile, it's sort of arbitrary. It's a sort of subjective measure of the material. But you should try to understand, like, when you're picking a material, what kind of deformation are you hoping for or trying to avoid? That's another consideration. Okay, everyone following along?
Yeah.
Okay. Okay, yeah, why is this important? Because all materials have a point after which they sort of break. The yield point and the failure point. Okay, yeah, I kind of explained these. Right. So yes, when designing parts, think about where the forces are being applied and how much forces are being applied. So if you have a sort of right angle part here, and you're going to apply forces from this direction, in order to support this part, you could add an additional brace here, an additional rib here. Or maybe if you know that you're making a wooden part and it has to bear some amount of weight, you could add additional bolts to it to make the piece stronger. Yeah. When selecting materials, you can always take a look at these curves to see how much deformation is possible for your part. And also, this also is, like, you can also consider this when trying to machine your part. Real world examples. So yes, this is what necking looks like. Look at the cheesy pizza over there. Basically, what happens when you stress that cheese, and you just keep lifting the pizza, the cheese is gonna eventually thin out and then break. That's what necking is. Imagine that happening to steel or aluminum. Isn't that hilarious? That is called tensile stress. Compression or compressive stress is what happens when you squeeze something. So basically on the stress ball, there's a force being applied from the thumb over here and from the rest of the hand over here. And so the middle part gets compressed and it bulges out on the two sides. Shear stress is what happens when two scissors are cutting. So these two blades of the scissors are parallel to each other. And so they apply shear stress to the material in between. Bending. So this popsicle stick got bent, and torsional stress. It's just when you're wringing out, when you're twisting something. So, how do you find material properties? Well, Google, of course. But MatWeb is a good source. MatWeb has a lot of different properties. And as long as you know what you're looking for, it should be an easy site to look through. Or always, you can always ask another RD member. Yeah, I just keep thinking of Young here, but I don't think he's very active right now. And yes, the CES EduPack. It's available on VLab under ME 2020. That's the remote desktop that you can connect to. Add tip of the day. Oh, let's see. Does anyone have any questions regarding materials, material properties, or anything? Is anyone following around? Okay. I hope you guys are asking questions in the chat.
We're getting a lot of good questions in the chat, yeah.
Okay, cool.
I guess one thing I could ask is, do these kind of stress strain curves also apply for like non-metal materials, like composite, like things like wood or I guess composites?
Ooh, okay. First of all, non-metals. So we discussed glass and rubber here, so obviously yes.
True.
But okay, wood is a sort of different beast altogether. Wood is made out of fibers, you know, because it used to be a living thing once. And so these fibers sort of act differently. Like they'll be strong in one direction and not as strong in another direction. Like there are a lot of materials like these that they have fibrous. Sorry, what was I saying? Like they'll have fibers, or they'll be like bundled together, and so they have strength in certain directions, and in another direction they'll not be as strong. Think about like a plank of wood. Have you ever tried breaking a plank of wood with your hand or something? Like if you had to try to break it along its length, it would be really difficult. But if you like strike it in the middle, it would be easier to break. You get it? So there is a word for these. It's called isotropic. So steel, aluminum. These are isotropic materials, which means their material properties are the same in any direction. And the opposite of that is anisotropic. Wood would be anisotropic. Glass and rubber are kind of wonky in this. I'm going to say they're anisotropic because it depends on the process in which they were made as well. Like there are a few different kinds of glass, and rubber also consists of sort of like stretchy molecules. And so I would say rubber is anisotropic as well. Does that answer your question?
Yeah, that was great. Thank you.
Okay, cool. Anyone else? Kyle and Keaton, if you guys are done answering questions, just let me know so I can move on.
Yeah, we're good to go.
Okay,
And,
cool.
and you're right, the glass and rubber are both amorphous and have different properties in different directions. They're uneven. So they're anisotropic as well.
Yeah, cool. Okay, so yeah, here we have a CAD tip of the day. Choosing your units. This is important because you might be working with international students here who might use the metric system. So yeah, you can change your units in CAD. Just these are in. I think they should be in properties. But yeah, like you can choose millimeters or inches and just stick with one throughout your project. Like often you'll have multiple people working on different parts. So like if you started off a new part in inches and you realized everyone is using millimeters, you can just change your material. You can just change like your properties. And in case you have to, you can also just scale your parts by 25.44. Okay. 3D printing. Yeah, this is particularly important because we use Cura. This software only takes millimeters. And so, like, a lot of times it happens that our students, they'll have like a part that is just made in inches, and then they'll have to convert it to millimeters. I think Cura itself has an inbuilt way to just scale your part. Yeah, this is the scale option. If you enter 2540%, then it'll just turn your inches into millimeters. Well, it won't turn your inches into millimeters, but it will give you the exact size you want. Because if you don't do this part and you made your part initially in inches, you'll just end up with a tinier part. Because it will think that 1 inch was 1 millimeter, and so on. Okay, it's time for a Kahoot. Oh.
I just got so excited, and then I realized we aren't allowed to play. Not we
Yeah.
aren't allowed to play, but we just shouldn't.
Okay, I'll
I'm
stop.
ready to see some crazy stuff, guys. Who's gonna be the best?
What is asking me? I'm not sharing my screen right now, am I?
Nope.
Okay, because Kahoot locked me out because I was inactive or something. Okay, I hope everyone has your phones with you. Like, just pull out your phone and go to kahoot.it in a browser. Okay, I'll start sharing my screen again. So just go to kahoot.it. Okay, can everyone see my screen?
Yep, we got you.
Okay, cool. Oh. Okay, hang on. I need to.
I had someone over the summer share what they were doing Kahoot, and they shared with sound, and it was deafening.
Okay, I have to mess with the settings a bit, so let me just turn off screen for a few moments. Okay, yeah. Does everyone see the pin?
Yep.
Okay, cool. Try to join
Yes, we
this game. Also, probably I should have mentioned this earlier, but please use your real name so that we can all know each other. Nicholas, please no black magic. Thank you. Okay. Yeah, we have 9 people. Is that all? Just Kyle, let me know when it's everyone.
So there's 16 people in the call. We have 3 people of her teaching, so 13, I guess. Assuming everyone joins.
Okay. Oh, okay. We have 30 people now. That's cool.
Nice, we did it.
Cool. So, yeah. Let's see. Time to start. I'm excited. Which type of stress is being created by breaking this popsicle stick? What does that
There's-
look like?
There's nothing like the rush of a Kahoot game, even if you're not playing it. The
Yeah.
feeling in my chest right now.
Yep, that is bending stress. Yeah, very good. Okay, on to the next question. Which type of stress is being created by twisting the can open to get the dough out? Somebody wants to make croissant.
I'll be honest, I didn't know that's how you open those cans.
Neither did I.
I think I went at one
I use a
can.
spoon always.
Well, okay, to be fair, I've never seen. I mean, I've never used such a can. And yes, that is torsion. Very good, guys. That is correct. What type of stress is created by cutting the dough or tearing it to make it into pieces? Oh, nice. Everyone knew that. Pretty good, guys. That is shear stress or tensile stress. Okay, what is the blue part of this stress strain curve called? Just to clarify, what is this blue part? Elastic deformation. That's right. Elastic deformation because it happens linearly, like the amount of force you put in, at least like a linear amount of stress. I'm sorry. The amount of force you put in gives you like a proportional amount of stretching or compression. And if you let it go, it goes back to its initial position. What are 2 materials that are most commonly used for 3D printing? PLA and ABS.
Nylon is used though.
Hmm?
I have used nylon.
Yeah, cool. We personally use PLA a lot, although I don't think I remember use ABS in rubber jackets. So blank equals reaction to blank. It's stress reaction to strain, or strain reaction to stress. That's good. Strain is a reaction to stress. Strain is what happens after a material undergoes a stress. Good. Carlos on fire, yo. What is stronger, aluminum 6061 or 7075? What did I say about numbers. Yep, that's good. Bigger number, better. It gives you one. Bigger numbers, of course. Which material is more ductile? Steel or aluminum? Steel, because ooh, I wish it still. Oh, there you go. Yeah, steel is more ductile because of how much more strain it can get, how much more you can stretch it, how much more you can deform it. Whereas aluminum does not deform as much. Of course, the energy required to deform steel is higher than aluminum, but you can deform it more, and that's what we're looking for here. And that's it, I guess. Oh, 2 more questions. What is more impact resistant, ABS or PLA? ABS is indeed more impact resistant. And I think we're on to the last question, y'all. What is the name of the point at which a material begins to fit plastically deform? The yield point, indeed. So that was the last question. And, ooh.
GG, Nick. GG.
I was fighting for points that entire time. I was like 7 points off the previous question.
Yeah, it does consider your reaction time as well. But it seems like all 3 of you guys got 10 out of 10 questions right. Yeah, well played, guys. Anybody got any questions? Okay, so just one last thing we've got to cover. It's the guides that we have. So we have 3 guides. I'll be covering one of these, and this is called the parametric CAD. There are 2 other guides called the CAD guide and the advanced CAD guide that we'll be sharing with you guys. Feel free to go over these like on your own time, at your own pace. And if you have any questions about these, feel free to ask us. Like, these are mostly about, like, they'll take you through making a part from start to finish, and like they'll explain certain tools along the way. But let's see, on to parametric CAD. Okay. Can you guys see the parametric CAD presentation?
Yes.
Yep.
Okay, cool. Special topic. So when you're making a design, a CAD design, that is basically your first draft. You might want to keep changing a few things here and there. Oh, what happens if I make this part longer? Or maybe I should increase the thickness of this other part. So we learned about sketches last time. Would you do you think it would be convenient if every time you want to change one value, you open up the part, you open up the sketch, and try to mess things around? So another way to adjust variables, or like measurements and stuff, is to create variables and assign values to those variables. And one way to do this is in Excel and sort of link it into your CAD. Anyway, you can like create a list of variables and name them whatever you want to, and you generally give them names such that it makes sense to you and the people you're working with. And like, so this allows you to directly change a part without actually going into the sketch or the part features and trying to edit it there. So you can just like type in a number and change the thing. Okay. Yes, inventor will reference dimensions and variables to make equations as well. So let's say you're trying to create a sort of rectangle, and you want this rectangle such that its width is always twice the length of the rectangle. You can like create one side and call it length, and you can assign the value for the other dimension as 2 times length. This way, all you have to do is adjust one parameter, and the rectangle always stays in its 2-to-1 ratio. And like this is just a simple example. Other things, like I'm sure you can come up with a lot of other things that you want to use this for. And it's not always fixed. Like, let's say you want to change the rectangle as well. You can just set it to like 3, or you can set it to like 3 times length, or 3 times length plus 5, just whatever sort of equation you want to put in there. And you can also use equations while you're creating your sketch itself. So over here, as you can see, we have like top equals to radius minus 0.25. So it seems like someone's trying to create a hole here or something like that. And if you want this thickness to remain constant, you can sort of just use the same radius but subtract 0.25 from it to get to this part. Or equations. Of course, when creating sketches and other kinds of features, it's important to know like why you want, like where you want your parts to reference from, and like what kind of references you want. So if you want, say, like the value 0.5, you could have numerous midpoints. But in this case, what you care about is the midpoint. This is like, okay, let's say you have a diameter and you want to find this midpoint. You could just pick the diameter and then divide it by 2, and that would ensure you get the diameter every time, even if you change that diameter. If you used another variable, let's say the distance between the top to this axis, then this answer would change if you had to, say, move the circle around. So think about what references you're using when you create your equations. Okay, everyone following along? Any questions? I'm sure chat will handle it. And so this is how you do this, a parameter box. This tiny little fx hiding on the top of your screen, or parameters, and manage. So this is where you can access all your dimensions. This is where you can create variables. You can just assign them properties and value. And you can also just rename and edit them over here. So over here, we look, see, we have a radius, height, middle. And you can just enter these over here. And here's another like cool thing. Like, you don't have to create the part first. Like, you can just create a variable first. Just name it, like say upper radius equals 2 inches or something. And then you can just go around creating the parts. And then when you want to apply the upper radius to something, you can just sort of like edit the dimension and type upper radius in here. And so that'll reference the upper radius that you've already created in here. Oh, I want to explain this. Creating new variables. Yeah, you can add a name. Just make sure your name has some sort of letters in it, because if it's just a number, like, the system will get confused. And of course, as I mentioned earlier, you can also use an Excel sheet. Sort of like you can link an Excel sheet with the particular part. Well, not just particular part, but you can also just like share among different parts. And so you can just open the same table in Excel itself, like type in variable names and values, and then it will just update in the part itself. And so, like, let's say you're creating an assembly that requires multiple parts, and they all have like a common axis or something, a common axle, let's say. Then you can choose that axle radius, like you can like decide that in Excel, and then when you want to say change the axle radius, you can edit it in Excel, and all of these parts will get updated accordingly. So that's also a neat way to do that.